Welcome to day 2 of the LSIC Autonomy workshop. We'll jump right into things. Katina, could you move to the next slide, please? Thank you. So just a reminder, some meeting logistics. Our main venue for questions and comments, and we have polls up, is Slido. So you can either go to slido.com and put in the code LSIC-autonomy with the password 2023 workshop, or you can scan the QR code on the top there, and that should take you to the right place. There's already a poll open. I think it's a great question about which pop culture autonomous system would you prefer to assist you on the moon? So if you're interested in joining that chat, please go there. And then as a reminder, the event schedule and program are both on our page, which is on this QR code on the bottom here. If you need help finding any of these things, any of the co-hosts should be able to point you in the right direction. Next slide, please. So with that, I'll flip it over to Autonomy Chatterjee to do some opening remarks and a summary of day 1. Autonomy is the LSIC Excavation and Construction Focus Area Lead. So he's way at the top there. Autonomy, are you on and able to help?
Yeah, hi, good morning. Yes, let me share my screen.
Yep.
Can you see my screen?
Yes, we can see it.
Okay, and so hi, good morning, everyone. Welcome to day 2. And as Danielle said, I work with the Excavation and Construction Focus Group here at APL. And first of all, let me start with a big shout out to you, Danielle, Katina, Sarah, and ENC and Extreme Access teams for this wonderful workshop. It's been great so far, and we will have more interesting things to see today too. So let me start with some advertisement and announcement. If you're not already familiar with our focus group, Excavation and Construction Focus Group, so we do a lot of stuff related to construction, excavation, as the name says, outfitting and assembly on lunar surface, and autonomy innovatively is a big part of our discussions. We have a subgroup on autonomy too, as you can see on this slide. And so we have well-attended monthly meetings on the last Wednesday of every month between from 2 to 3:30 Eastern Standard Time. And these meetings are well-attended, very informative, and sometimes our participation goes to 3 digits. And so if you have not signed up for this ENC focus group, please do so. The website appears on the screen, and the mailing list. So we have close to 1,000 members, and we're growing. Moving on to announcement. Ascend, as you know, is a premier conference organized by AIAA. So this year, 2023, Ascend will be held in Las Vegas from October 23rd to October 25th. So a few folks from here at APL LSIC, including me, we are organizing a roundtable session titled Moon 2035, Living Off the Land. So this will be held on October 25th at 11 a.m. So we will have roundtable discussions on 4 new and emerging and important topics: lunar surface manufacturing, lunar proving grounds. We've already started discussions on this topic in earnest. Responsible lunar presence and value chain. So if you're attending Ascend, if you're around on October 25th, do consider participating in this roundtable. It will be very informal and informative, and autonomy, of course, will play an important role in many of it, especially in lunar surface manufacturing and lunar proving grounds. So coming back to this workshop, we had a great day yesterday on day 1. We had great discussions on some core aspects of autonomy, namely situational and self-awareness, collaborative systems, human-machine teaming, and so on. So we'll build on those topics on day 2 today. And today we will focus more on the lunar applications of autonomy, especially in the areas of excavation and construction and extreme access. We'll talk about mining technologies, the role of autonomy in site preparation, excavation and construction, lunar perception and sensing, autonomous navigation, etc. So format will be just like yesterday. We'll have panels, networking discussion, and breakouts. So finally, before concluding, when it comes to autonomy, especially in the areas dear to me, excavation, construction, assembly, and outfitting, here are some of the thoughts we gathered over the course of time from the community, from our own analysis, and from what we heard yesterday. So one thing community members, they always say is that we need a clear definition of levels of autonomy needed when it comes to construction and assembly, when it comes to extraterrestrial or lunar surface, in our case, lunar surface operations. And this was pointed out yesterday also by a few members. And just like what we have for self-driving cars. And then, as you all know, and as was pointed out yesterday, there is a spectrum between teleoperations and full autonomy. So you have teleoperations on one side, you have 100% full autonomy on the other side. Full autonomy is some way to go. And some speakers pointed out yesterday, semi-autonomy may be more manageable. And so where we are on the spectrum depends on our risk tolerance, what is the state of the art, and what is the need? Do we really need full autonomy? So this is the discussion we will continue to have. And then when it comes to construction and assembly, especially, shared control between humans and robots will be absolutely essential. And we talked about it yesterday in the context of human-machine teaming. And also for construction, mining, etc., cooperative robots, swarming will be crucial. As you know, when you have many robots, when you have a swarm of robots, it brings in redundancy, and redundancy is very important. All smart systems, including human body, they have built-in redundancies, as you may have noted. And also, what kind of cooperation you need? You need swarming as the way ants or termites operate, or teaming as the way, for instance, a football team operates. So these are the discussions we'll continue to have going forward. And also, for lunar surface construction, predictive maintenance is very important. As someone put it yesterday, autonomously responding to unanticipated failure. So predictive maintenance is going to be very important as we are developing technologies and building infrastructure. So in this context, autonomy, digital twins are going to be very important, and also learnings from terrestrial experience with the Industry 4 paradigm. Terrestrial companies, they're barging ahead in this area of predictive maintenance using autonomy and digital twins. And finally, going forward, in addition to assembly and construction, lunar surface outfitting and manufacturing will become more and more important. And so the role of autonomy in these areas will assume more importance as we go forward. So yeah, so these are some of the thoughts. Some of it we will discuss today and we will discuss in near future. So with that, let me conclude, and back to you, Danielle. Have fun.
Thanks so much. Really appreciate you doing that. What a great summary and summary of the expectations for the upcoming day. So we're gonna move on to our next session, which is lunar applications in autonomy. So first up, we have our panel. So I guess I'm not sure I saw Chris online, so we'll try to get that sorted out. But for right now, Terry, are you online and able to do a quick introduction?
Yes, I'm here. Good morning, everybody. This is Terry Fong. I'm the Chief Roboticist at NASA Ames, and I'm the Deputy Manager for the Viper Lunar Rover. I've been working in autonomy for many, many years. Until recently, I was actually in the role of Senior Scientist for Autonomous Systems for NASA headquarters, and I've done quite a bit of work with APL and the LSIC since they got started.
Thanks. Al Hassan, are you online and able to introduce?
I am. Can you hear me?
Yes, can hear you.
Perfect. Hi, I'm Al Hassan Yassin. I'm a senior researcher at the Applied Physics Laboratory and a lecturer at Johns Hopkins University in computer science. And also I lead the conversation in autonomy for excavation, construction, and extreme access. And a lot of the conversations around AI, robotics, autonomy. Happy to be here and be part of the conversation.
Thanks so much. And Chris, are you online? All right, looks like we have some people working on that, making sure maybe there's technical difficulties going on. But for right now, Terry and Al Hassan, thank you for participating in our panel. So obviously this is kind of the lunar side of our autonomy workshop. We wanted to incorporate the moon, obviously, since we're LSIC. So thank you guys for being the representatives of this important piece of the workshop. So we'll start kind of with some of the more simple questions, just kind of what does autonomy look like right now in a lunar context? And then what might you see it looking like in the next 10 to 20 years?
Wow, so that's a really great open-ended question to start off with. I think we had some discussion, a couple of different breakouts yesterday that I participated in about what is the overall focus for autonomy, and of course, from a NASA point of view, NASA's used the definition that autonomy is the capability to achieve goals while operating independently of external control. So for a lunar system, or in particular, let's say a lunar surface system, the question is, how can it accomplish goals independent of having to be, remotely operated or remotely supervised from the Earth? In the case of a mission like Viper, that occurs primarily in the area of fault management or anomaly response, especially for those things which are best handled on board, maybe because it requires very rapid response, maybe because it's something that requires board data that can easily be downlinked to Earth. And so in the context of missions like Viper, worrying about things like how do you recover from loss of signal, it might be multipath, might be obstruction, things that are best handled on board in terms of managing comm, might be focused on that area. So I certainly think that those kinds of things, anomaly response, fault management, those are sort of the obvious things. That's probably the near-term thing. As we look towards the future, of course, the question is going to be, are we going to try to carry out missions that require, more productivity by some measure of productivity? Maybe it's driving speed, maybe it is number of tasks executed per unit time, and those things may also require onboard capabilities, because it's possible you could do things more productively on board than trying to always loop in people on ground control.
Thank you.
I fully agree with what Terry's saying, and I also think from a perspective of technology, I mean, it's really hard to really dictate what 10 years looks like on the lunar surface. I mean, if you look back on any technology that we've ever kind of tried to predict it, we've always gotten it wrong. Knowing 5 years, 10 years, I mean, if you know that, that's like, you know what stocks to go through, that's like a very hard question. But I do think that at least from an autonomy perspective, thinking about like the long-term and short-term perspective, I think from a short-term perspective, there will be robotic systems, autonomous systems that are somehow intertwined within a human operator present. We won't go fully autonomous from the start. That's a very hard problem to tackle. I think initially it's going to be these autonomous systems, maybe robotics, maybe communication systems that are teleoperated, or somehow a human is in the loop as they go about doing their operations. And then in a natural progression would be for them to continuously to take less of a human in the loop perspective. But I don't think that's an immediate, and it may not even be a 10-year perspective. I think that's a very long course of action. But communications is huge, robotic systems, navigation, systems that will effectively help develop the habitat itself, because that's the first thing that you want to develop going into developing things that are useful for, let's say, from a scientific perspective. We won't do science immediately. We need to actually develop the tools to be able to do those such things.
Yeah, certainly. And I think that talks a lot to our conversations yesterday on, full autonomy on the moon or not, and bringing in that idea that we need to build up this beginning infrastructure with things like comms and position, navigation, timing before we can really get a solid system to create autonomous systems up there. So that's very good points. Thank you. So moving on to the next question, what activities on the moon require autonomous operations? So kind of like what we've been saying, it's present a little bit of everywhere. And I guess our question kind of turns into, is there anything on the moon that wouldn't require autonomous operations? Oh, Terry, I think you're muted.
Yeah, sorry about that. I think there's also the question of what particular functions or particular capabilities might benefit, or maybe the flip side is would not benefit from the use of more autonomous capabilities. I think certainly we at this point in time know a lot about how to make things work in an autonomous manner, at least with many types of machines, and certainly with various kinds of robots. But the question is always going to be, certainly I believe in my lifetime, is going to be what's actually required. I think that if you're on a NASA sponsored mission, again, NASA's approach has always been, well, let's talk about the requirements, first and foremost. And if autonomy is something that is required because maybe it's something that can only be done through the use of autonomy, whether that's on board or the system level or whatever, then it's something that people are going to develop and test. But if you can have a different system design that says, well, okay, we could do it autonomous, or we could do it in a different way that doesn't require any autonomy whatsoever, that's where you get into all these trades. And again, I think it comes back down to the requirements. So go back to the question, if there's a particular type of thing you're doing on the surface, let's say, oh, we need to have a robot take measurements in a permanently shadowed region without communications to Earth. That has to be able to safely move, make those measurements, come back, and eventually communicate those things at a later point. If that's the mission design and requirement, then of course it's going to be autonomous. But I think it kind of goes back to the whole question of really what are the requirements of a particular task or mission.
Yeah, I would second that conversation. I would also add on thinking about like the problems that will be faced on the lunar surface. Naturally, you want everything to be autonomous. You don't want humans to really have to do too much other than like, let's say, what's the point of having an astronaut up in the lunar surface? The best use of their time is effectively doing science. It's not to move sand from one area or move regolith from one area to another area, for example. That's like not the best use of time. So naturally you would say, well, almost everything will be autonomous or to some extent. But then you can also ask this question, well, what things can we not do that, like right now, let's say on Earth, that can't be done autonomously? And that goes back on, let's say, for example, like actually doing science. Some things require manual labor, some things that are very intricate, that require not necessarily a fully autonomous system, maybe requires a human present to make a judgment call or something. I think judgment calls might be a thing that isn't fully autonomous. And that's more of a human kind of dictating, how we utilize the different systems, for example. Or thinking about, for example, from a perspective of, let's say, health, for example, right? Like maintaining astronauts' health if a doctor needs to see them or something on board. That's a hard thing to really develop autonomous systems for, although we have thought of this before. So that's really the premise behind it. But I'm all for figuring out how to best utilize autonomy as best as we can, so that we go away from actually having our astronauts do every little part of construction, of science, right. Like, we need to take away some of that capacity that they have to more useful things, like actually doing science, exploring potentially. And I do think that from an autonomous system, we've demonstrated time and time again here on Earth that we can do a lot of very useful things with autonomy. Right now, we have autonomous groups for excavation, construction, and extreme access, but I do see that I envision that autonomy plays in a lot of these other subgroups that we've talked about with the LSIC.
Yeah, certainly. I think it's a very diverse topic, which can cover a little bit of everything. So I like all of your comments, and particularly I think that this idea of, our concept of moving forward in technology, making more autonomous systems may not necessarily be the best way of moving forward. And Terry, I think that's kind of what you were getting at. So yeah, I very much agreed. Thank you guys.
Yeah, if I could add, I really
Thanks.
think that we often get into these arguments about, to be autonomous or not to be autonomous, and that's not really the right question, because I think that if we need to create something that is autonomous, and granted there still are lots of technical challenges for that, but if we need to create something that is autonomous, we can focus our efforts on doing that. And so it's not really the right question of like, oh, should it or should it not be autonomous? I think, again, it's really trying to think about what is the best solution for addressing a particular problem. What's the trade for making use of autonomy at whatever level it is, whether this is low level safeguarding or high level, task level operations. I would also point out too that if you look at our experience with the ISS, the vast majority of robotic operations on the ISS are no longer involving crew. They're being done by ground control. Partially that's because of the speed by which those systems operate, and there's this I think really good analysis that says, well, look, we don't want to waste our crew time doing that because it takes a long time to set up, carry out, and tear down. So we should do that through ground, and we should do a lot of preparation, planning, detailed planning for those command sequences. So maybe the same can be said about the moon. I do think obviously that we look at Mars, and Mars is a whole different thing because it's just not practical to try to do every command cycle with Earth in the loop, and so therefore we do see more autonomy being used. It has been used for a long time on Mars.
Yeah, that's a good point, especially, as we're moving from the moon to Mars, trying to adapt those technologies. Is it I don't think it's always a direct, okay, copy and paste over to Mars. There are a lot of differences between the two. So recognizing that and realizing that we can't just move everything direct is very important. Awesome.
Yeah, I would add on to that perspective. Just like we do lunar proving grounds right on Earth, the moon is effectively a proving ground for Mars. I mean, the technology, the capabilities that will be developed there, and effectively is ways that we're going to think about, well, we have latency, we have these things. These are kind of characteristics of Mars as well in some capacity. Of course, it's a lot more extreme in that sense, but I do think that those types of tools, right now we can envision what they might look like, but when we're actually up there and when we start to develop these procedures and frameworks of how to really best dictate this, it will, of course, guide us towards how Mars might look like, but also guide us towards how we might do things differently, effectively here on our planet. I mean, that's the premise behind all of NASA's kind of perspective, is not just, oh, here's just one thing and then it's just used for that perspective. If there's dual use perspectives, if there's ways to integrate that knowledge to something else, that's to the benefit. And I do think that the moon has such that perspective. It really will add on to how we change things here and also potentially do things, operations in Mars, and hopefully future perspectives.
Yeah, to your point, I think there's a great advent of modularization when it comes to building spacecraft and capabilities and technologies these days. So that's definitely a good start to that. So moving on to the next questions, is more towards the environmental side. What challenges about the moon make autonomy more difficult than terrestrially? And then this leads into the question of, are we even able to send state-of-the-art terrestrial autonomous systems up to the moon right now? And what would make that possible or impossible?
Wow, those are actually two of my favorite questions. I think one of the things to first consider for the moon is how challenging the environment is overall. I mean, and not to belittle sending missions to Mars or other places, but the moon obviously has very, very difficult conditions to keep systems alive. And so I think from the point of view of deploying autonomous capabilities, being able to operate under lunar conditions is driven oftentimes by do you have the right sensors to be able to perceive the environment? Do you have the ability to carry out particular planned activities through appropriate onboard computing, or perhaps like Viper is trying to do, make use of some offboard computing in case of Vipers on the ground, but in the future maybe that could be gateway or could be some computing in a habitat. I think it is certainly driven, as I was saying, by the fact that the environment can be exceptionally challenging. You think about operating in permanently shadowed regions. Do we have appropriate sensors? We rely heavily on passive sensors for most space missions, except for recently, I guess, sort of terminal phase EDL where you may use LiDAR. But by and large, the workhorse systems we use for sensing the environment are camera systems. Okay, well, fine. Cameras do require some source of light, some source of illumination in order to be effective. And so how do you operate if you don't carry your own lights? And even if you carry your own lights, I think about the design of Viper's operations. It's hugely challenging in the polar regions where you have really long cast shadows and long cast self shadows. So that's certainly I think a big issue to deal with. The lunar environment is far more difficult in many respects than Mars, and I think again having the appropriate sensing and computing to deal with that is certainly going to be a challenge for all missions, not just for near-term ones coming up.
Yeah, definitely. Thanks.
I think Terry definitely said that very well. I would add on think about like the temperature differences, when you're going from completely, sunlight and then all of a sudden there isn't. I mean, think about how fast that change in temperature occurs, where you have tools and operations that need to be present there, where power is a factor, where the different components is a factor, and that they have to continue to do that. The terrain is, like you can't take everything into account, right? Like we have proving grounds. We have an idea of what we're looking for or what we can conceive, but it's also limited on what we can't conceive. So developing autonomous systems that can naturally adapt to those situations, and that's a very challenging thing. How do you continue to adapt or learn, let's say, the terrain that's forever changing? You see a rock that's not, maybe next time it's a different rock, or it's a crater or something completely different. A lot of the thought is, how do we utilize the tools properly? Like AI is great, of course, but is that the only way we can do autonomy, right? When the training is a factor, we can do autonomy without AI, for example. So those are definitely huge areas, and sometimes we might not see it full-heartedly, that simple things like temperature, for example, is a factor. But this is the point of the LSIC anyways, is we can communicate these types of information to, let's say, a new organization that hasn't gone through this process, or is just starting off, so that it becomes a community interaction. But I fully agree with Terry. Brilliant comment.
Yeah, I think to answer your second question about sort of redeploying or making use of autonomous systems technologies, whatever level you're talking about, whether these are algorithms or software, or maybe it's just like overall system design between terrestrial applications and the moon. Certainly, we would like to be able to reuse what we use commercially and state of the art and state of practice on Earth. But it is challenging when we think about just the environmental differences. I look at some current missions which are either ready for launch or near ready for launch that involve planetary rovers. Moon Ranger at Carnegie Mellon, Lunar Vertex at EPL spring to mind, and both of those systems rely heavily upon things that work very, very well on Earth. They both make use of software like the Robot Operating System, or ROS. They use high performance computing. They rely on high resolution imagers, small level. And these are not, when I say high resolution imagers, these are small board level cameras. All these things work really well on Earth. We see these all the time in terms of all kinds of different robotic applications. How well will they work on Earth for a lunar day duration constrained mission? That is something that might last 7 to say maybe 12 days at sort of the outer duration. I think we're waiting all to see, can they be successful in that time? 7 to 12 days really is very little time for like dealing with just, one major system anomaly. And just getting something checked out and operating fully, we look at past planetary rover missions. And of course you could say, well, NASA is a very, deliberate, slow moving, very cautious in all mission phases, including initial deployment and checkout. But 12 days, think of where we were, with Curiosity or Perseverance after 12 days. They were not rushing across the Mars surface. They were still going through checkout. So I think we do have to kind of calibrate our expectations of what may be feasible in terms of just taking something terrestrially and redeploying it for the moon.
Yeah, certainly. And this conversation, it completely takes me back to our Lunar Proving Grounds workshop that we had a month or so ago.
Yep.
And a lot of the takeaways that we got from that was we need to be testing full system missions and at duration. And that was just such a big point of, if you're planning to go and survive the lunar night and deal with things like the lighting, the harsh lighting, and deal with things like temperature change, like Hassan, you mentioned, you need to be testing all of these things in the same boat and making sure it works together. So very good points, thank you. So the next question kind of goes back to what we were discussing at first of on the topic of infrastructure and what infrastructure we would need to support autonomous systems on the lunar surface. So I know we had mentioned things like comms and position, navigation, timing, but is there anything else that's very important to autonomous systems on the moon?
Well, I think certainly anything that gives you better understanding about the environment, whether this is at the level of high resolution maps that are created in some way. We think about areas that we can see well from orbit. And of course, there are motivations for creating different kinds of remote sensing. I mean, that's one of the reasons why ShadowCam was launched, to be able to see into PSRs, hopefully better than we can see elsewhere, still relying on passive imaging. I certainly think that the extent to which that you have higher resolution and complete terrain models can be very, very helpful, at least for surface operations. In addition, I think that anything that allows a system to exist for longer durations is very helpful infrastructure. Maybe that has to do with some sort of way to keep a system alive through the lunar night, or to provide additional power. A lot of the systems we're designing these days are solar powered, for good reasons, just because of the associated complexity, lead time, paperwork, whatever you want to think about it, associated with the use of radioisotopes, even RHUs, add on a lot to a mission. And so if there's a way that infrastructure can provide additional power or shelter, and think of that in terms of like thermal shelter, I think that could be really beneficial infrastructure, because then you have allow systems which can operate longer term, and that's not just autonomous ones, of course, but that allows them to actually be more productive.
Yeah, certainly.
I would add on to that just computational resources. I think that's a huge thing that, of course, autonomous systems require such things, but like think about every other system that is going to be present there. Or like currently we have high performance computing systems for pretty much every kind of autonomous systems that we have in some capacity. So that's going to be a huge factor from the habitat, from the rovers, from all the other sensors on board. So that to me is literally like one of the most challenging ones. Of course, comms, I mean, that's a huge factor, but you need to be able to actually compute. You need to be able to actually perform the tasks that you aimed and you're planning to do. And being requiring that to be sent over is also very costly too. So more thought definitely has to be addressed there. How is it, maybe can we do maybe computational resources at home and then send some information back, or is there something that requires, like, how do we minimize what type of computations that the system requires there on the surface compared to things that maybe can be done here and then just transmitted or sent back? So that's a huge factor, because you can send information that's one resource that you need to figure out, but also do we need to be able to compute things as, let's say, for example, the terrain is forever changing. Do you need to relearn how to navigate, or do you need to adjust when you navigate through different areas or something? And I think that's a huge factor, because it doesn't just rely on autonomy. It's literally every component that's present.
Yeah, I really like that comment there about the use of offboard computing resources. We see terrestrially that there's a huge set of things that we rely upon these days, where computation is not only done on board, but rather is done off board as well. You think about every single one of us who uses a navigation service on our phones. You look at Apple Map or Google Maps. That computation is not done only on board. In fact, most of it is done off board, and it's not just the computation; it's the offboard data as well. And so, looking at opportunities for us to create system designs that are supported by infrastructure, and that could be lunar-centric infrastructure on the surface in orbit, but it can also be infrastructure back home, here on Earth. I mentioned earlier that Viper, has offboarded some portions of its computing. I don't know how many people are aware of this, but Viper's flight software design explicitly has computing and software. The flight software split between onboard and on the ground, so that we can take advantage of faster commodity computing on the ground and lots of data that would be just, frankly, too difficult to put on board Viper. And I think that is probably the right approach going forward, because not only does it allow you to take advantage of higher performance computing, but you can reuse that over and over again. It can be reused in parallel for multiple missions at the same time, but obviously it can also exist from mission to other mission. And so that would be, I don't know, I'm not sure if I'm recommending creating a data center on the moon, but I mean, that still could be, I think, a very important thing for people to think going forward from like interoperability point of view. How do you have computing and storage resources that can be accessed by these future lunar missions?
I really like the perspective that you alluded to from computation, but also from a memory perspective. Think about how much data is going to be, like any rover, like on any given day, that's going to go up there. Think about how much data it's going to be collecting, either transmitting back, or either sending it to some habitat or back on Earth. That's any days, gigs, terabytes. You can think of the sky's the limit effectively there. It's just so much information. Is that stored there? Is that sent back? Is like that's a huge thing that we really need to address accordingly. And I think it's to your benefit if you have more data. I mean, the premise behind autonomous systems is you have enough data to be able to do something about it. So it's not against you, but like, how do you utilize those resources accordingly and not, reinvent the wheel every time you go up there or every time you do some operation itself.
Yeah, I completely agree, and I feel like this has been a topic that's come up over and over again with some of my research, and in that, are we going to have enough computing power in order to do some of the autonomous operations that we want to do on the moon? It's definitely a prevalent issue that I think a lot of people don't think about. I mean, someone says, okay, I have this, great backflipping robot, but what you don't see is the servers upon servers that are running computational analysis to get it to do that. So very, very important points, yes. So I'd like to flip over. We have a couple questions that have come in on Slido. One of the top questions was on how can we make autonomy a more useful tool? So they mention, for example, mutable locus of control or different levels of abstraction. I don't know if you guys have comments on that.
Yeah, to make it more useful. I think just like pretty much any technology, in order to be useful, it has to be something that you understand well, number one, and number two, can has been implemented in a way to meet requirements. And so what that means, of course, is that if you're going to require some particular autonomous feature, autonomous function, that you have to be able to describe it well, and that you have to be able to build it and test it so that people have confidence that it will perform as expected. And I mentioned earlier, Viper has a need to be able to try to autonomously recover COM, and that's because it's driven by Viper's mission design. Viper operates in continuous real-time communications with Earth, and so the system has to be capable of trying to recover COM if it disappears unexpectedly. And that's everything from making decisions of, do I just repoint the antenna, the high gain antenna, which is very directional? Do I move? And how do I move? Do I try to basically move backwards, undo the last motion because maybe I happened to move and I went to a situation where there was obstruction to that line of sight COM? And so, I think that, for Viper, a lot of tremendous amount of thought has gone into the design of the autonomous recovery sequence. What does it do on board? What order does it do things on? And then a lot of testing has been going on to basically verify that it will perform as expected. So, to me, any autonomous function falls in the same sort of bin. Can we describe it really well, and can we test it so that we're confident it will work?
Yeah, certainly. And I remember recently in the news, Voyager 2 lost contact with Earth because it was pointed 2 degrees off. And, they were mentioning needing to wait until October to reconnect when it had that backup system to repoint at Earth. So again, something very important that I personally never would have thought of, when you're thinking of, okay, I'm going to send a spacecraft out there and just hope it's pointing in the right direction the whole time. So very important. Alsan, do you have any thoughts to contribute to that?
Yeah. So you asked like the use case scenarios or useful. We have a notion that we develop these autonomous systems and they have this, this this operation, this task, this thing that we care for. But oftentimes when we design them, there is some thought and it should be addressed. What other things could we potentially utilize them for? And not necessarily just here's a tool, you're going to, let's say, completely fix it on the rover or on the autonomous system. Maybe from a perspective of we can interchange, let's say, different parts or different sensors because we can use them for something else. And that's a thought that happens all the time, actually. It's maybe you have, let's say, an arm or some system that's attached directly to the rover. It's not just used for picking up rocks, for example. It could be used for digging. It could be used for, so that modularity perspective definitely gives that what type of uses, how do you make them effective? And I also think that's limited on our capacity to imagine how we want to use these systems. Sometimes we're in emergency situations, and you often look at, well, what do you have and how do you utilize what you have? It's impossible to take everything into account, of course, but that's this is the engineering, this is the thought behind all of these tools going into it. It's not just I kind of force it to do one thing, and in some cases maybe that is a tool that is only able to do that one thing because it's just so like it's just a required perspective. But there are often times we have these systems that we develop that we might need them for other cases, and that's to our benefit. I hope that kind of addresses it, but that, I mean, it is a hard question too.
Yeah, certainly it is. It's an interesting, again, going back to what you guys are saying, like defining it is a difficult process in the first place. So how do you consider something useful? But very, very good answers to that question. It looks like our last panelist, Chris Zachny from Honeybee Robotics, might be on. Chris, are you there? Able to give a short introduction in our last 10 or so minutes of the panel?
Absolutely. Really apologize for being late.
No worries.
Tough morning. So I'm VP of Exploration Systems at Honeybee Robotics. I run division of around 200 people dedicated to developing planetary robotics. We are based in Altadena at the foothills of beautiful mountains. And we just had an earthquake and a hurricane. So recovering from all of this.
Yeah, thanks so much for joining us. I'm glad you were able to hop on.
Absolutely.
So I think there was a lot of questions on questions and comments in the chat on the division between the near side and the far side of the moon, and how they're like two different worlds. And there was one question on if we're kind of developing additional considerations for operations on the far side of the moon that we might not be thinking of on the close side, or even if the poles are kind of involved in that, being a weird area that drops in and out of comms and has some strange night and day cycles. So I don't know if you have any thoughts on that.
Well, I certainly think that it goes to the question of what is the particular operational environment for a mission, and based on that environment, what are you doing to make it feasible to carry out operations? I mean, you could say that subsurface void, whether it's a pit, skylight, lava tube, also is radically different than the near side surface. You could say that the near side surface equatorial is different from near side surface that's towards the poles, and those are all true. And the fact that you may not have common some of those locations, is something that you could choose to deal with through the system design. You could make it so the system doesn't require continuous communication, or you could deploy common infrastructure, relays, to the subsurface, an orbiting comm relay, and so it's not, in my mind, really a question of do you choose to use autonomy as the solution to everything. Autonomy certainly is one tool in our toolbox, but it really comes back to understanding what are the operational constraints for a particular mission.
Yeah, good points.
Yeah, if I could add to this,
of course.
The use of autonomy. If you have long-term assigned, can you hear me? Sorry.
It's a bit of an unstable connection, looks like, but you're back now, hopefully. If you try turning off your video, it might help with bandwidth issues.
Is this better now?
Yes, much better.
Okay.
Thanks.
Yeah, I wanted to mention that the use of autonomy is very much application dependent. What sort of mission you actually have at hand. Some missions don't really require that much interaction with humans here on Earth, and things take significantly longer. For example, processing of data through instruments. Well, you acquire data, and then you sit on the surface and you do your own thing, and then every so often you think of, hey, I found this or that. At that point, we take our own time to figure out what to do next. So in this case, do we need high-level autonomy? No, we don't. But then you have a sort of other missions. Even I would argue on a mobility front. It would be nice to have autonomy, but this is going to be driven by available power. And sensors and computation, computers and so on, they do take a lot of energy. So we are going to be, if we want to have a fast roving, mobility system with bunch of sensors, this is really going to be dependent on how much energy we have. We may have a super duper autonomy, but if we don't have energy, we cannot go very far. So autonomy has to be, considered in terms of all other, resources. And based on from what I've seen, power / energy is a limiting factor here.
Yeah, I definitely agree. Someone had brought up the point yesterday when I asked how like hierarchical elections worked in multiple machine systems, and someone mentioned that the leader would be the rover robot who had the most power. So that's definitely a great consideration for us here. Alasan, did you have anything to add to that one? If he's still, oh, he's just entered the waiting room. Al-Hassan, are you back? All right. Well, while he gets things back up, I guess we'll flip to another, and this is kind of a question that I'm pretty curious about, is human safety on the moon being a big concern. And especially as we're moving towards having sustained presence on the moon in the Artemis 3 mission and everything, building a lunar base camp, how will autonomous systems help us protect the astronauts who will potentially be spending a long time on the moon?
I think that's a great question because of all of our discussion of the use of the moon as a proving ground for sending people to Mars or frankly any other place that's further away in the solar system. Certainly, we can do a lot to support human safety, crew safety on the lunar surface in very similar ways to the way we do that now for the ISS. But if we are really trying to look at the future where humans might be 20 to 40 minutes round trip, at least in communications, not even talk about any other sort of support or response, but at least just communications in the situation where they're on the surface of Mars, then obviously that changes a lot. And so I would contend that in terms of autonomous systems, anything that helps with sort of like basic safety, health, well-being, in terms of like monitoring or actions that can support crews so that crew can operate without relying upon, many people at mission control, just trying to monitor their vitals, so to speak, would be helpful. Maybe that's in terms of even say wearable systems to help prevent falls in the same way that some researchers today on Earth are doing that for elderly. Not trying to claim that crew are elderly, but obviously it is difficult, especially when you're in a pressure suit. To deal with. I fell and couldn't get up, so to speak. And so maybe some autonomous wearable device will help signal, hey, there's a trip hazard here, or you're starting to fall. I'll try to keep you upright.
Yeah.
To add to what Terry mentioned. I think some of the examples could be where something that initially may have been operated by astronauts could actually also be done robotically. So for example, you have a lunar rover, lunar buggy, right? It's operated by astronauts. But the same buggy could potentially be made autonomous or robotic or operated from Earth with a robotic arm at the back, which could also be operated by astronaut or robotic. So if there is an accident somewhere, you can imagine that this robotic arm would help get the injured astronaut onto the buggy. And while the second astronaut is tended to help this astronaut, the rover could be fully autonomous and driving everything back to the habitat. So combining building in autonomy into systems that are normally human tended or human operated would provide this second level of redundancy in case something goes wrong. So if you take one step further, one can argue that all systems should have dual or triple operation mode, right? Operated by a human on the surface of the moon, operated by somebody from Earth, and or full robotic autonomy with some bounds. So at that point, you do as much as you physically can. There will be obviously extremes which you haven't foreseen. But one item that could be actually interesting to do while on maybe not on Artemis 3 but further out is to run a simulation where I know it's expensive time for astronauts to be on the surface of the moon, but this is also quite important. And anyone that has went to the field, we do this kind of stuff. Pretend that somebody's injured and set aside half an hour, for example. Somebody got injured on the moon, and what would it take, real life, to take injured astronaut back into the habitat? At that point, this would tell us exactly what we need to do for next time.
Yeah, definitely. I think a lot of this, I agree that we should have kind of redundancy, and that was a big theme yesterday as well. And doing what you suggested of having, one person on Earth looking at things, one person on the moon looking at things, and then a full autonomous system altogether would be fantastic in terms of making sure that humans stay safe on the moon. And I also think it goes back to our conversation from session 1 on trust in autonomous systems. It's can be hard for people to say, okay, I'm handing my health and safety over to a robot. Let's hope things work out. And whoever was programming that was making the right decisions and thought of everything. So yeah, very, very great points. It looks like we're kind of at time. So do you guys have any concluding thoughts that you'd like to share, or if not, we can move right on.
A last thing that I wanted to say, oftentimes we design these systems and we think about these systems in the like I call it the happy zone, or the zone that we're very comfortable with. And there's like this zone that is very extreme, like emergency situations where everything's talking to each other and the bandwidth is like impossible to send any information, right? So those are the things that we sometimes really forget, and these are the tests, these are the where you can evaluate, like a costly simulation when everything is operating and running might give you what those extremes are, because sometimes it's really hard to think about. Like in an emergency situation, something happens at the moon, does every single rover send information back? Is it even possible for someone to even interpret that? Like that's a concerning thing. How do you dictate the let's say resource allocation perspective there? What is what should be thought of as high priority compared to something else, for example? These things often are not necessarily forgotten, but there are very interesting situations that we may not fully kind of appreciate or give enough time to, because we're always in this zone that, oh, we're comfortable here, we understand this. But oftentimes we may, those extreme situations, I'm not saying that we should, I want it to happen, but of course these situations might happen, and that's the planning perspective. But thank you so much. This is great conversation overall.
Yeah.
Yeah, Daniel, I think just one final thought I have here is really just this question of why it seems to be so hard and so difficult for us to deploy increased autonomous capabilities in space. And I would say that part of that really is driven by the fact that autonomy is no different than any other new technology. The question is, what are the barriers to adoption of that technology? And by and large, I think in terms of autonomy, the barrier is, do we have enough confidence? You can talk about this in terms of trust, in terms of V&V or whatever, but do we have enough confidence that it will perform as needed? And if there's anything we can do to make that more readily achievable, maybe that is more extensive, more comprehensive testing that somehow can be done faster and cheaper. Maybe that's the thing that eliminates the barrier. But again, I really I'm not convinced that autonomy is in a unique category all by itself. It really is, I think, just highly reflective of any sort of new technology where there are barriers to its use. And again, just trying to understand those barriers and figure out how do we eliminate them or at least reduce them, is what will really advance the field. So, but thanks. This panel has been great.
Yeah. Last thing I quickly want to say that even though in some cases we do not think about autonomy yet, we should develop our robotic systems and hardware specifically to take into account future autonomy. Because once you fly something and you haven't thought about autonomy and you don't have a hardware supporting it, that's it, you're done. So you need to essentially put right processors, right sensors that will eventually enable you to deploy full autonomy, and software only gets better. So let's not forget about it. Whenever we design a mission or spacecraft or rover, let's think about autonomy, even though we're not thinking about deploying autonomy on day one. All right, but let's not shoot ourselves in the foot early on.
Certainly. Yeah. Thank you all so much for your participation in the panel. You've had wonderful thoughts, and I think they'll be added to the community, and they'll spark conversation at our networking discussion. So thank you so much for participating. All right, welcome back, everyone. I hope you had a nice 3 minutes. We're able to get some coffee or something. So we're going to move now into our presentations for the lunar applications and autonomy session. So first up, we have Doug Morrison. I see you're on. Thank you. Katina, can we flip to the next? Oh, okay, that works. Doug, are you able to share your slides, or would you like us to?
Yeah, no, I'm hoping that's going to happen if I press that button. Now press this button. Now press this button.
Yep.
Then
Yeah, we
all
see them.
happens. Is that true? Yep. All good.
Yeah.
Then I'm good to go. Okay. Quick introduction then. I have 40 years experience in the mining industry, hard rock mining industry mostly. Mostly in underground mines for the first half of my career. Second half of my career in surface mines, as well as tailings and waste management, environmental issues. And of course, it's all to do with complex operations underground, safety, security, backup plans for everything. So that's where I'm coming from. So a bit different background from most of the rest of you, and a few more years than most of the rest of you as well. So here we go. So everybody thinks about mining on the moon, and this is typically what people think about when you think about mining. Big trucks in big open pit mines, but we also have very big equipment in underground mines. This is the kind of problems that you have with large pieces of equipment in underground mines. So this is not a problem-free environment. And it's certainly not a problem-free environment when you have very large underground excavations and very large machines. Can you all hear me so far? Is that okay, Danielle?
Yeah, sounds great. Thanks.
Yeah, great. Okay, so those are the kinds of problems we have, the kind of equipment we have. And this is all the other things you need to do in an underground mine. It's much more complex than surface mines. And the constraints are completely different. And one of the things I want to touch on is, instead of focusing entirely on technology, to actually begin to think much more about the constraints, because the moon is a seriously constrained and hostile environment. So this is a kind of workhorse machine that we have in the mines, 35 years old now. all started around about 1985. And before that, when I started my career, the black and white photographs on the left were the kinds of machines we were using. Very small, manually operated, very dangerous, etc., etc. So everything became much safer, and much more productive. But it also became less efficient, you'll be surprised to discover. And of course, all these machines, we were changing from pneumatic compressed air machines to electric, hydraulic, and diesel type equipment. And of course, everything we do underground is explosives and not available on the moon. So that's a constraint. And the other big constraint we have with this kind of equipment is that the equipment on the left, the old small stuff, basically we spent 15% of the time moving the equipment and 85% of the time moving the payload. Whereas the equipment on the right-hand side, the big new productive, very powerful machines, they spend 90% of the time moving the machine and 10% of the time moving the payload. So that's a much less efficient system. And that's why we had a little challenge in Canada about moving stuff way, way back. You can overcome the payload problem if you just have lots and lots of machines. But the other problem with those big machines is they take a huge amount of energy also. So those trucks, 75% of the energy that is burned by that truck is used to move the truck. And 25% of the energy is used to move the payload. And that ratio is not a good ratio at all. And it's certainly not a good ratio for the moon. And so that's just another little thing we did in the last little while, because a simple machine, and this one on the left-hand side was the target challenge, NASA challenge, to move 10 kilograms of regolith, 10 meters laterally and 3 meters vertically. And the Laurentian University team, mining school, used an Archimedes screw to do that, which is technology from 265 BC. And it moved the necessary material in 11 minutes. And none of the other teams, who were all using relatively modern 19th and 20th century technologies, were not able to move 10 kilos within 1 hour. So the 365 BC machine did the job when the modern equipment did not. So it's a clue as to where we need to go to find solutions. Certainly when we made this transition in 1985 to the big machine on the top right, we could have taken the other option, which was to go to a continuous system in the bottom right. And that's 3 times more, or at 20% of the energy, so it's 15 times more effective than the one above. But it wasn't actually configured for the underground environment at the time, and so it was bypassed in favor of the machine on the top right, the scoop ram. And so the other thing you want to consider is the difference between automation and autonomization, because I do think the discussion about to be or not to be autonomous on the moon is not a necessary conversation to have. It absolutely has to be fully autonomous on the moon. And that means that we have to make systems and develop systems to be fully autonomous on Earth before we even think about sending them to the moon. And that should be the primary focus of what we do, is accept the fact that it has to be fully autonomous and figure out what we have to do to make that happen, and then focus our attention on the activities that have to be made autonomous. The difference is simply this: if you have automation, you get rid of the cab driver, get rid of the cab, but all the other factors stay the same. Whereas if you take the option of autonomization, you have the opportunity to completely change the design of the equipment, which is not designed for people at all. And that means you can eliminate the direct labor operating it, you can reduce the maintenance labor, increase the process efficiency. You can do all those things when you make the mental decision, we're going to make the whole thing completely autonomous, rather than in any way automated or human being controlled or overseen. We simply cannot afford to send people to the moon to oversee the activities of machines on the moon. So the upshot of this piece is just to say, if you make autonomous systems, they can be 15 to 30 times more cost effective than the ones that we have right now. And of course, that kind of improvement in performance is good for the mining industry, but it's not relevant for the moon at all, except that we can make those pieces of equipment 15 to 30 times smaller and less mass than the ones we use right now. And that's a really good thing for getting those things lifted off the Earth and sent to the moon. So really what I'm suggesting is there's things that we used to do in the past that are very helpful to us, going back in time and in principle. And that's because it's a simple, robust, effective system. Ancient histories, in a history, we did lots of really big stuff in resource-constrained environments, and the resource constraints were severe, but humanity built really, really big stuff in the Iron Age, in the Stone Age, in the Copper Age. This was done with very, very few resources except human beings. And we know we can now replace the human being effort with autonomous machines, and we can accomplish really, really big stuff. But it's about the constraints that you have to work within. So when you look at what we have with the moon, it's a very hostile place to be. And you have surface radiation that we have to protect people against. The regolith is a very aggressive material, so you have health and consumable impacts, you have equipment wear impacts. This is a very tough place to be. This is not a comfortable place to be. And since I have spent most of my career in underground mines, I'm very comfortable with an underground environment. And that is a built underground environment, one that we have managed the creation of to perform to the standards that we need to make it safe and secure for people to live in or work in. So that's what we need to do. We need to move to these kinds of systems. For me, even before we start about infrastructure on the moon, we have to have infrastructure on the moon before we have a sustained presence. We're not going to build a sustained presence with people on the moon. That stuff has to be there. At least a base case has to be in place and operating reliably and securely before we send people to do any further expansion of that base case. So, for example, you have to have a reusable landing and liftoff facility. You have to. And that has to get through to bedrock. It's very difficult, it seems to me, to compact the regolith to make it acceptable. Think of what's happened to the recent takeoff that we had with SpaceX, and they've already damaged their own very, very heavily constructed landing pad. And is it going to be reusable? And that's what we have to create on the moon. Because right now we've spent billions of dollars to build rockets, and rockets that have nowhere to go except take off from Earth and land back on Earth again. And that's not really the point. So clear the regolith out of the way, groom the level surface, deflection barriers. We can't have the plume distributing huge amounts of regolith all across the lunar surface. And then we can start to focus on building a safe, secure, habitable facility and consumable stockpile storage facility. And we also have to have backup plans. We have to have travel emergency refuge stations with atmosphere, water, food, and heat, because if we're going to have anybody moving around on the surface, we have to recognize you have to have a backup plan for all of that. And so where we've gone with our thinking, just bringing in mining type thinking, mining engineering type thinking, is, yeah, you got to have, you've got to engineer lunar infrastructure. You have to have an overland transportation system for commuter. Rovers are trying to go to new places that we haven't been to before. But once you want to go back and forth from A to B and B to A again, that's a commuter type system. And that's not the same as an autonomous rover finding new places to go. Yes.
About
yep.
1 minute. 1 minute, Doug.
Okay, here we are. This is the last slide, really. Regolith harvester, sorting and packaging. You've got to have a novel drill system, which we've developed, and we're just finishing off the IP now. So we can drill holes of any length and size, anywhere. We can groom the bedrock, and we can build underground facilities in the bedrock. And that creates a much more safe and secure place to be. So here we are. Modern earth moving technology really isn't helpful, takes a huge amount of energy, and is very heavy on maintenance. And we don't have either of those on the moon. The lunar surface is very hostile. We have to have highly effective systems, reduced in size and mass for Earth liftoff. We can look to what technologies humanity has used in the past to build the simple, robust, energy and time efficient systems that we need to make completely autonomous. And we can even look to non-mining sectors. I'm not saying that mining has all the answers. We used to do very well with agriculture. And we can take some of those models, equipment, the old-fashioned equipment, horse-drawn equipment even, but we can make that autonomous. And that becomes a useful tool for us on a resource-constrained environment like the lunar surface. And so that takes you to utilization and processing to avoid Earth analog models. The moon is not the Earth. And we can't simply transfer technologies from the Earth to the Moon. It's too complex and variable. And lunar resources, we have to focus on the resources that exist there and develop simple, reliable processes that we can use on the Moon itself. And that's it. Thank you for listening.
Thank you so much, Doug. That was a great presentation. I really like the historical references of we've done such large things and without this high tech autonomous system. So wonderful presentation. I'd like to direct if you have any questions for Doug, please put them on the Slido, and we'll have a 10-minute Q&A for all the presenters at the end of the presentations. So next up, we have Julia Badger from NASA Johnson Space Center. She will be presenting on Gateway and the autonomous control of human spacecraft. Julia, are you online and able to share your slides, or would you like us to?
I am online. Can you hear me?
Yes, we can.
All right, let's see. Let me share here. Okay, can you see my slides?
Yes, we can.
Excellent. All right. So my name is Julia Badger. I am the Autonomy and Vehicle System Manager for Gateway at NASA Johnson Space Center. I'm going to talk to you a little bit about what Gateway is. So this is a conceptual picture of our Gateway, our lunar gateway, which is a space station that we're putting up around the moon in a non-rectilinear halo orbit, so a real long orbit. It's meant to be kind of the cornerstone of the Artemis program, in the sense that we're going to have people and a spacecraft congregating at the gateway. It's meant to be sort of a gateway to sustainable operations, both on the moon and then also thinking forward to Mars. And so our gateway is, I like to say it's kind of the rustic camping outpost that our ISS astronauts will go to for fun. They'll spend about a month at the gateway or on the lunar surface, kind of in that vicinity at first, and moving to kind of a little bit longer stays. And so the gateway will be uncrewed for about 90% of its life, about 11 months a year. We're also thinking a little bit differently from a standpoint of operations. So we have our ISS here. It's huge, low Earth orbit. We are in almost continuous comm with it. It has been continuously crewed since for the last 20 some years. And it is serviced by a group of people that there's at least 6, I think, on console 24/7, 365. Usually the room looks like this when we actually have astronauts awake. We're sending up about 900 commands per day to the ISS to make it go. So we're not going to be able to do that when we have Artemis going. There's just going to be a lot of stuff happening all at the same time, particularly when the gateway isn't crewed. It's still going to do science and need to have the same sort of complex systems that support human life available and ready for the crew when they do come up. So the 900 commands per day are a reasonable thing to expect that we will have to do from a gateway perspective. But we just don't have the operations staff or money to do that long term. And so our gateway ConOps is really going to be more of a breaking the link with ground and thinking about operations on console about 8 hours per week. Even as we are first launching the gateway, right now is planned for late 2025. It is expected that in 2026, we're going to start not servicing the gateway overnight with a ground mission control center. So there's definitely going to be some need for autonomy. So because those commands don't go away, what we are doing is we're introducing a new system to our gateway. It's something called the Vehicle Systems Manager, or VSM. It's essentially part of our distributed hierarchical autonomous control architecture that's going to allow us to do the tactical day-to-day mission management and other types of things on board. So those 900 commands a day will be things that will be essentially fed to the VSM and its partner software applications on board to be able to take care of the vehicle. VSM is founded on this concept of distributed hierarchical control, where we try to separate domains of control to stay where they need to based on the information that they can see. So we've tried to push down control and delegate control to the lowest level that has the visibility to make the decisions, and then control authority rises up only when the visibility is across different domains. So for example, we have modules that will be built and added to the gateway over time, very similar to how ISS was built. And the vehicle systems manager will essentially only take care of things that have some sort of impact across the different modules. The modules themselves will have module system managers that will handle any internal impacts as long as they don't affect things that kind of happen at the vehicle level. So this idea of data and model abstraction then allows us to basically try to maintain a limited scope of what we could do with each part of that control architecture. We're trying to make it feasible this way. Our main functions that we have for VSM is there's five. One is the human interface, essentially, with the vehicle that I don't have listed here. But the other management functions have various levels of automation that is possible. So we have mission management and timeline execution, which essentially has the idea of what are we doing when do we turn on a payload, when are we having RPOD, when do we communicate back to ground, what's the ground station I'm looking at. All of that's controlled by the mission timeline. Resources, because they are limited, are essentially controlled at the vehicle level. So power, comm bandwidth, network bandwidth, thermal load, those sorts of things are vehicle wide. And so we manage those and optimize those up at the VSM level. Fault management is only if we are managing faults that cross boundaries. There's not a ton of those. Power faults obviously tend to do that in things that are emergencies like fires or leaks, thermal loop issues, those sorts of things that happen. Some big things that happen are the faults that we would be looking at the vehicle level. So we have a faults management function as well. And finally, vehicle control and operations. Battery control across the stack when we're in Eclipse, doing things like deciding whose Eclipse or life support system is prime, those types of, and comm, a lot of the comm link generation and failover is all controlled up at the vehicle level. And so we have applications that do that as well. So quick day in the life of our gateway. We do have a requirement, which is a Mars forward requirement that is aiming for 21-day automation, a 21-day separation from ground control, and it can be in either a crewed or uncrewed configuration. And so when we are in that kind of realm, we expect that the ground support is minimal, that they are doing strategic planning for what is it that I'm going to want the gateway to achieve over the next few weeks, and providing goals and kind of an intent essentially to the gateway to be able to have the gateway then go and figure out and do its own thing. The gateway itself then, we kind of have this modeled as an observe, orient, decide, act type of loop. So it does loop back around at the end there, receive data, and then get written commands. But we are thinking about providing, constraints and consequences to our human operators, making sure that they understand what's going on in the vehicle at any given time if they needed to pop in. We'll be analyzing our health, the tracking goals, determining states of the system. We'll be then, from a decide standpoint, creating our own timelines, allocating resources, part of the timeline, those sorts of things, and then executing all of that, and then ensuring that we're also communicating back to everything. We have a set of module system managers, and those acronyms on the side are just the indicators of the different modules that we'll have on there. And so those are partners to the VSM and actually executing the types of things that the vehicle needs to do, and they maintain the health and status of their own module independently, as it's basically a delegated authority from the VSM.
Julia,
In these 21 days.
You have about 2 minutes left.
Sorry?
And there was also
Okay.
a request to hide the share screen Zoom at the bottom of your screen. I don't know if you see that.
Oh, I think I can do that. There we
Thank you. Awesome.
Yeah, no problem. The mission timeline, all of these, we would expect during these 21 days for them to be pegged to full autonomy. And we would expect that the human operators, if they did look at the system at all during this 21 days, they would really just be receiving data and reports and defining these mission goals. So the idea here is that we're pushing this all the way forward. I think this is my last slide. And so this is just this is a concept of what we are doing right now. We're expecting to launch our VSM when the first 2 modules launch, the Halo and the PPE, at the end of October in 2025. And we're actually getting ready for our critical design review at the end of next month. So I'm happy to take any of your questions at the end. Thank you.
Thank you so much, Julia. What a fantastic presentation. I know I feel like Gateway has been talked about so much, but I haven't heard much on the specifics, so it was really great to hear some of that. So our next presenter is Neil Dantim from Colorado School of Mines. So he'll be presenting on the autonomous site preparation, excavation, compaction, and testing, otherwise known as aspects. Neil, are you able to share your slides or? Oh, awesome. Cool.
I think so. Is that working?
Yep.
All right. Thank you.
Thanks.
All right. So this is a multi-institution group. Most of us are at the School of Mines, also involving MTU and some industry folks from Lunar Outpost and Bechtel. So the goal is to develop an autonomous lunar construction machine to prepare a lunar landing pad. So we are expecting to demonstrate site preparation in a test environment we're producing here on campus. The system should operate autonomously, do state estimation and task and motion planning, robustly, efficiently prepare the site, and then we're putting together an infusion plan to put this on a path to flight. So the site itself is 10 meters in diameter. We don't have any prior map. We need to fill craters, remove rocks, level the site to plus minus 1 degree, smooth it to 1 centimeter RMS, and then compact 90% down to 30 centimeters. The robot is limited to 83 kilograms, so that would give us the same reaction forces as a 500 kilogram robot on the moon, 1/6 Earth gravity. Can't use GPS, no GPS on the moon. And then we need the system to operate with push button autonomy, since a teleoperation would not be practical. The key challenges for this system are the low lunar gravity that reduces the amount of reaction force we have available. So we need to minimize the amount of regolith that we move, balance the cutting forces from moving regolith with the traction forces that are available, and then are limited to only moving loose, low density regolith. And then the system needs to be autonomous. So the idea is to prepare a landing site before humans would arrive. So we wouldn't have a human there to teleoperate. The system itself would have to autonomously plan the necessary steps. So we're constructing a lunar regolith test bed here on the Mines campus in the Earth Mechanics Institute. We do have a smaller test bed that we've used for some initial tests. So this will be the 10-meter diameter site. Using a regolith simulant, CSM LHT1, and then the rocks will be pumice to sort of match the weight of a rock on the moon. This is what the aspect vehicle looks like. So there is a chassis, dozer blade on the front, compactor on the back, and then we're designing wheels as well. The chassis itself comes from Lunar Outpost, their Hound rover. So at the top is what the rover looked like at the start of the project. At the bottom is what was delivered to our campus about a month ago. So it's a differential drive, skid steer, each wheel independently driven. On the front, we have a multi-purpose bucket blade. So this will push or lift regolith and rocks, smooth regolith. If we need to rip regolith so we can move it at lower density, we can do that. And then we're designing this in conjunction with the wheels, so we get enough traction. We're designing rigid and compliant wheels. So the rigid wheels are 3D printed, so we can very quickly test different configurations. And then the compliant wheels will potentially offer more traction. The folks at MTU are developing the vibratory compactor. So a bunch of pins that vibrate down into the regolith and then vibrate back out to compact it. So the benefit here is that this would require or need less weight than traditional compactor designs that are just very heavily pressing down on something. This is the development of the compactor. So the current testing units, what we expect the rover mounted design to look like, and then a potential infusion design. Here's a block diagram of our state estimation and autonomy approach. So no prior map, we start out by surveying the site, then plan for the steps the rover has to take. So moving rocks, moving regolith, compacting areas, find the motions for each of those steps, and then execute and do this iteratively until we've prepared the site. We're doing visual SLAM for navigation and state estimation. So we don't have any existing navigation infrastructure on the moon. And then the regolith and low gravity can lead to additional wheel slip. So odometry would be less reliable. So to do SLAM, we'll use rocks as landmarks, segment from the RGB image, and then use depth image to find their positions. And then get poses of rocks in the rover concurrently using an extended Kalman smoother, and then use the slip dynamics model to compensate for the rover wheel slip. So we've tested this prior to the Hound rover delivery using a ClearPath Husky Intel RealSense camera, and in the regular simulant. We place fiducials to get the ground truth, and we're able to localize the robot and map the rock. So continuing this, we would integrate rock detection and integrate with our planning and autonomy. We're taking a task and motion planning approach to autonomy. So task planning is finding the high-level actions or steps for the system. Typical approaches would be search or constraint solving. Motion planning is finding the paths, motions to execute each of those steps. Typical approaches would be sampling-based or optimization-based motion planning. So we've been doing this for a while using a combination of constraint solving and sampling-based motion planning, starting for manipulation type of applications, but moving into some mobile robot navigation applications like this as well. So we developed a task domain based on some discussions with people who understood what site preparation was supposed to look like. So modeling the different actions, so moving a rock, smoothing, compacting, and the dependencies between those. So you run the planner on this task domain, you get the sequence of steps the robot has to take. And then we need to find the motion plans for each of those steps. So from the map we get through visual SLAM, we construct the 3D scene in which the robot has to move, and then find the motions by planning through that scene. So the path for infusion would be scaling from this small prototype system to human scale site preparation, so up to 100-meter diameter pad, which would need additional support and equipment, and then putting the system on a path to flight. Okay, so our goal is to prepare a lunar landing site. We're designing this autonomous construction machine. Chassis is the Lunar Outpost Hound rover, designing a multi-purpose bucket, vibratory compaction system, doing state estimation using visual SLAM, and autonomy through a task and motion planning approach. So thank you.
Thank you so much. Really appreciate that. That was a fantastic presentation. So I think at this point we'll move into a quick Q&A. We don't have too much time, but I did want to ask, and this is to all the presenters. So Doug and Julia, if you're online and able to come back and answer. You all had such a wide array of applications for autonomy on the moon. But I guess one of the things that kind of kind of comes back is you need some sort of perception and sensing of your environments, whatever it may be, if it's on Gateway or if it's on the lunar surface. So to everyone, what kind of instrumentation and sensors might your autonomous system need in order to fulfill the tasks that you're starting with?
Maybe I'll start since I was focused on the lunar surface. A lot of the kind of sensing technology that we want to be able to use is actually with autonomous cars already, for example. The difficulty that we have in implementing those are things like changes in the weather, pedestrians who do silly things in front of vehicles, etc., animals and cats, and all the extraneous things that happen in an urban environment. And we don't have any of those on the moon. So the moon is a much easier place to do autonomy than is the planet Earth on surface. The second easiest place is actually underground in mines, because we actually have a constrained environment where many of those activities, unplannable activities that happen, events that happen, can't happen. We don't have a lot of people down there. Everybody's down there to do something very specific. They all know what the machines are for. And it's a very, very disciplined and constrained environment, which we do not have on surface. So many of the kinds of things that we already are thinking about doing, or have actually, companies have developed, autonomous cars, for example, we have a lot of that already, but I do think we absolutely have to have the gateway to help manage those kinds of communication systems. In the mines already, we use drones quite a bit now when some of our autonomous vehicles can't communicate in the regular way. And so we use a communications drone that will fly out from one of the vehicles to reconnect the data flow between the two units. We can't do that on the moon because we have no atmosphere. And so what that would mean is maybe there's a place for micro rovers that will actually recreate those connection systems, data communication systems when we need them. So, but I'll leave the answer to some other folks.
Thank you. Yeah, Neil or Julia, do you have any additional comments?
Sure. So yeah, the sensors we typically see on mobile robots would be LiDARs and depth cameras. You know, it's the reduction in cost of LiDARs in the last decade and a half has made things a lot easier for roboticists, right, compared to work before using just RGB or stereo cameras.
Yeah, good point. Julia, anything to add?
Not really. I mean, we're using essentially the types of sensors that we would see on any spacecraft. So, you know, we're looking at temperature, current, flow rate, humidity sensors, those sorts of things. So nothing special. Yeah.
It's interesting how you would still kind of need the same perception and sensing technologies for an orbital system, even though the environments are completely different. So there was another question for you, Julia, on Slido, and it's how do you verify and validate the autonomy you're developing for Gateway?
That is a great question that would take, you know, a couple hours to answer. But we are doing quite a lot for that. We're looking a little bit into formal methods to understand kind of the interconnections between the various parts of our architecture. So assume guarantee contracts are part of what we're using and looking at, both operationally verified as well as looking at how to kind of audit the systems, doing their testing of their requirements and how that interacts with our integrated testing. But then we're putting everything together, and we're using an approach where we do analysis on low fidelity models of the software and the systems, and try to hit that with as many types of use cases as we can, but in particular risk-informed use cases. So we're doing like assessments of the fault action impacts when we're looking at our fault model, instead of necessarily digging into all the possible, paths that it could go. We're looking at which ones have the highest risk of being timing dependent, for example, and using that as input into kind of what are the parameters and how many use cases do I do that are kind of in this area. After we do the analysis, which will be hundreds of cases, we will take edge cases and important cases from that analysis and then put it on a higher fidelity set of facilities. So our software verification lab here at JSD, and maybe even the Grail, the avionics lab. And so we'll kind of pick the level of fidelity that we need and reduce down the cases and then do tests on those, and then kind of refer back to analysis to make sure that we're seeing reasonable comparisons across the high fidelity and low fidelity and hit things that way. Hopefully that's a good overview.
Yeah, wonderful. Thank you. And thanks for not making it a couple hours answer. So I think we have time for one last question. This one was for Neil. If the people were interested in how positionally accurate aspect is, and generally how the navigation works. Is it based on visual localization, landmarks, mapping kind of thing?
Yeah, so we're using the rocks as landmarks. So we first segment those from the HSV image. So you get each rock in the image, and then we have it's a depth camera. So we get depths for each image, and then use that as positions and in a visual SLAM system to localize the robot and concurrently map the environment. As to accuracy, I'll have to refer you to Andrew Petruska, who is working on that part of the system.
Wonderful. Yeah, thank you all so much. I think we're about at time, so we're going to move into our next break here, but really appreciate all of your presentations. There were such varied aspects of autonomy on the moon, and I really love to see that spread of applications. So thank you all very much. With that said, I think we're going to move into our lunch break now. So we have an hour. There will be a lunch poll available. I believe it's up now. Yes, it's up now. So if you're able to scan the QR code and hop on and take that real quick, there are only 3 questions. Otherwise, we'll see you back here at 12:45. Thanks.